Okay, we are ready to look at this very important theorem that we'll be working on and adding to throughout the semester. The book calls it the equivalent statements. It's essentially the statements that are equivalent to a matrix A being invertible. And so let's talk about that. If A is an n by n matrix, so square, then the following statements are equivalent. And what do we mean by equivalent? That means they are all true or they're all false. So it's very important when we say statements are equivalent. That means if any one of these four statements is true, then the other three must be true. And if any one of these four statements is false, then the others must be false. And so that's a powerful connection we have there. And we're going to prove this theorem. And we're going to essentially prove by a chain of implications, sort of a circular reasoning, if you will. We will assume that statement A is true and prove that B statement follows from that. Then we will assume B is true and show that C follows from that. And then assuming C is true, show that D follows. And then finally, assuming D is true, we'll show that A follows. And we get these connections, right? So they're all connected. If one, kind of like dominoes, right? We have dominoes in a circle. We knock one over, all of them are going to knock down. That's sort of the idea behind the proof. Okay. So let's look at this proof. I think it's instructive and helpful. I know many of you are not used to seeing proofs in much detail. We've had a little bit of proof already. So let's take a look at this. The first step, then, I'm going to assume A and show that implies statement B. So we're going to assume A. We're going to assume that the matrix A is invertible. And thus, you know, we talked about the fact that this is the notation for the inverse. This inverse exists. Not all matrices are invertible, right? Some are non-invertible, or what we call singular, and they don't have an inverse. But since we're assuming A is true, we have this fact. Now, I'm going to let the vector x be any solution to the system AX equals 0. So when I say, you know, AX equals 0 has only the trivial solution is what we're trying to prove. Notice that this is the matrix notation for a system of linear equations. So A is the coefficient matrix, X, these are the variables, X of 1, X of 2. This is a n by 1 vector. And this is the 0 vector. These are the constants. And remember, when the constants are all 0, we call such a system homogeneous. So another way of saying it, that, you know, this homogeneous system will have only the trivial solution. Now, it's important to note that the homogeneous solution, a system rather, always has the trivial solution. Right? If the vector x is 0, then that's going to satisfy, right, this equation. And so that's true. But remember, we can have non-trivial solutions. Right? There's possibility of having infinitely many solutions. But what this is saying, that in the case where A is invertible, we will have only the trivial solution. Okay? So the way to prove this, we're going to multiply by the inverse on the left. And we've basically shown this before, essentially, in solving systems of linear equations in a previous lecture. But I'm going to do this. Notice that the multiplication is defined in each case, because both of these, AX and 0, are n by 1, right? A is n by n times n by 1, which is n by 1. And so A inverse is n by n, and I can do that multiplication. Okay. Of course, over here, I can do this multiplication, and A inverse times 0 vector, well, anything times a 0 vector, remember this is n by n, this is n by 1, so I get the n by 1 0 vector. Right? So, you know, A times the 0 vector gives me the 0 vector. Any matrix multiplied by the 0 vector gives me the 0 vector. What about here? Here I'm going to use the associative property of matrix multiplication and regroup. Can't change the order I'm multiplying in, but I can regroup. And what do we realize about this? A inverse times A. That's the identity. That's the definition of an inverse. And then what happens when I multiply the identity times the vector x? I just get the vector x. Okay. And there's the proof of the first part. I'll just, we're not done with the whole thing, but there's the first implication, right? Because we were trying to show what? If A is invertible, then this system has only the trivial solution. And that's what we've shown. We have only the trivial solution. Okay. So now we'll move to the second phase. We'll assume B is true, and we'll prove that C follows. Now B was what we just proved a minute ago, but now we're going to assume this is true, and then we're going to prove C, that the reduced row echelon form of the matrix A is the identity matrix. Okay, so here we're going to assume that x equal 0 is only solution to AX equals 0. All right, remember, we always have the trivial solution, so it would be wrong to say there's nothing to prove there. X equals 0 is always a solution to this system, but it's only that is saying something more. And what I want to look at just is look at the augmented matrix for this system for a minute. What's it going to look like? The augmented matrix, remember, we got the coefficient matrix of A, and so A, I'll just say, you know, the coefficients in the first equation we'll say of A11, so it's the coefficient of x sub 1 in the first equation, coefficient of x sub 2 in the first equation, so on, all the way to what? A sub 1n, because A is n by n. And then A21, A22, and so on. These are all the coefficients, all the way down to what? AN1, AN2, ANN. Okay, and then the augmented matrix, remember, we add on the constants. And what are the constants in this case? They're all zeros. All right, there's my augmented matrix for the system. Right, this would be the coefficient matrix, and there's my constants added on. Now, what do we do to solve the system? We would use Gaussian or Gauss-Jordan elimination, and we're going to put this into the reduced row echelon form, so use Gauss-Jordan elimination. Okay, but I submit to you that we already know what that's going to look like, because we're assuming that x equals 0 is the only solution. What would that look like if x equals 0 were the only solution? Well, I would have to have a 1, all right, for x sub 1, 0 x sub 2, all the way down to 0 x sub n equals what? Equals 0. This would say x sub 1 equals 0. And then I would have 0 x sub 2, 0 all the way down to 0 x sub 2 equals 0. And so on, right? Down to this last one here. Right, x sub n equals 0. So this would be x sub 1 equals 0, x sub 2 equals 0, x sub 3 equals 0, all the way down, right? So that's going to be our reduced row echelon form, because we're assuming that x equals 0 is the only solution. Okay. But what I just want to show, what would happen if I were to eliminate this column of zeros in this process? Well, the reduced row echelon form for the what's left, which notice what's left, this is just the matrix A. And clearly, then the only difference is, right, cut off that column is just going to cut off this column, right? These zeros, any row operation I do, this column of zeros is never going to change. I can never introduce anything other than zeros by doing any row operation. And what is this resulting matrix here? It's n by n what? It's the identity matrix. And so what we have is clearly that the reduced row echelon form of A is the identity matrix. And that proves that portion. So A implies B, B implies C. Now we got to do what? Assuming C is true, show that D follows. Okay. So C, we're going to assume that the reduced row echelon form of A is the identity. And then we're going to prove that then in that case A is expressible as a product of elementary matrices. So this is where our discussion about elementary matrices is going to come in. So I'm going to assume the reduced row echelon form of the matrix A is the identity matrix. Okay, if that's the case, then what we can take A, and if we want to put it into its reduced row echelon form, then we should be able to do that, and then there exists a sequence of elementary matrices and I don't know how many of these elementary matrices there are. I'm just going to denote them with subscripts, though. There'll be the first one we'll call E sub 1, the second one E sub 2, and then all the way to, I don't know how many we have, let's just say E sub k. Maybe there's k different elementary matrices, such that what? So what are each of these? So each row operation, so if I'm going to take the matrix A and I'm going to put it into its reduced row echelon form, what am I going to do? I'm going to get my leading 1 in the upper left-hand corner, right? So I'm going to multiply row 1 by, let's say I have a 2 in the upper left-hand corner. I'm going to multiply row 1 by half to get a 1 there. And so remember what happens. If E1 is obtained from the identity by multiplying row 1 by half, and I multiply on the left times A, that will perform that operation, right? We were talking about that in the last video. That will perform that operation. And then what, now I get a 0 beneath that leading 1, so I add a multiple of row 1 to row 2 to get a 0 there. And maybe E2 does that. And so if I multiply by E2, again on the left, times E1A, that will perform that row operation. And so on. So by multiplying, remember, by successively successively by these elementary matrices, right? So this will be our sequence of row operations that we do in transforming A from transforming A into its reduced row echelon form. So that will be a finite number of steps. We'll finally get to this E sub k, and the result will be the reduced row echelon form. But we're assuming that is the identity matrix. So it must be true that we can do this. We can take a sequence of elementary matrices, multiply them, and get the identity. Now, real important, we also showed in the last video that elementary matrices are invertible. So since elementary matrices are invertible, and I'll just say, and their inverses are also elementary matrices, then we have the following. So here's what we're going to do. So I'm going to start actually with this last row operation we did. This would have been the last row operation to finally put A in its reduced row echelon form into the identity matrix. So this elementary matrix has an inverse, and its inverse is an elementary matrix. So I'm going to multiply on the left both sides of this equation by the inverse of E sub k. So that's going to be E sub k inverse. Okay. And E sub k dot E sub 2, E sub 1 A, and E sub k inverse times the identity. All right. Now, of course, if I group these two together, what's going to happen right here? E sub k inverse times E sub k. That's just going to give me the identity. Okay. And then I'll have, identity times whatever E sub k minus 1 is here. It will just be E sub k minus 1 all the way down to E sub 2, E sub 1a. Over here, when I multiply, though, what E sub k inverse times the identity, that just gives me E sub k inverse. Okay. Now, what's going to happen? Now I'm going to multiply by the inverse of E sub k minus 1 on the left. So I do it here, and that will peel away, essentially, the next elementary matrix here, but it will add it here to the left. And keep building to the left. Right? And I'll continue all the way down until I get multiplied by E sub 2 inverse, and then finally E sub 1 inverse, and I'll be left with A all by itself here, and in order, E sub 1 inverse, E sub 2 inverse, dot, 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 all the way down to E sub k inverse. So by multiplying on the left by e sub k inverse and then e sub k minus 1 inverse and so on, all the way down to e sub 2 inverse, e sub 1 inverse, I get to this point, right? These will get all peeled away, turned into the identity matrix over there, and they'll build up over here from going from right to left. Okay, but what do I have here? A is expressed how? As a product of these matrices, but these matrices are what? Also elementary matrices. So this is a product of elementary matrices. And that's what we were supposed to show. Now this product of elementary matrices is not necessarily unique. You know, there are many different row operation that you can do, sequences of row operations that you can do to get A into the identity. It's not unique, but nonetheless it is a product of elementary matrices. All right, so the last leg then is assuming D, show that that implies A. So D was what we just proved, so we're going to assume that A is expressible as a product of elementary matrices. But again, elementary matrices are invertible. So if we're a product, if we have A is expressible as a product of elementary matrices, it's also expressible then as a product of invertible matrices. But we also know another theorem that we talked about before, and that is that also a product of invertible matrices, all the same size of course, is itself invertible. Right? So if A is equal to a product of elementary matrices, it's also equal to a product of invertible matrices, which makes A invertible. And that brings us to the grand finale. I'll put a big square for that. I don't know. That was the last. Right. That brings us back to A. Okay. And that proves our theorem that these four statements are indeed equivalent. Okay. Now, some of you, hopefully, if you're still paying attention, real important though, in the midst of this proof, I want to come back and take a look at this statement. We know that if A is invertible, then this statement is true. There's a sequence of elementary matrices such that we E sub k all the way down to E sub 1 times A is the identity, right? So this is the sequence of elementary row operations that basically transforms A into its reduced echelon form, which is the identity, again, if A is invertible. So I'm going to come to that to show you how we can then use that fact for finding an inverse of a matrix. So that's sort of the hidden nugget in the midst of this proof. So we know if A is invertible, right, that there exists this sequence of elementary matrices. Okay. Now what I'm going to do to show us what we can do from this, I'm going to multiply on the right this time by A inverse. Okay, both sides of this equation by A inverse. Okay, of course, I times A inverse on the right gives me A inverse. Here I'm going to regroup, right, this way. What's A times A inverse? That's the identity, right? And so I get this statement. So I want you to compare this right here to this right here. And what you'll see is, look at the E sub k all the way down to E sub 2, E sub 1. The same sequence of elementary row operations that converts A to its reduced echelon form, to the identity matrix, right, will also convert what? The identity matrix into what? The inverse. So there's the trick. As we're doing the row operations on A to reduce it to put it in reduced echelon form, which should be the identity, that same sequence of operations will transform the identity matrix into the inverse. Okay, and we get an algorithm, right? Essentially, the way we'll do it is we'll adjoin the identity matrix to our matrix. So if our matrix is, say, 3 by 3, the identity matrix is also 3 by 3. We now have a 3 by 6 matrix. And what we're going to do is we're going to use the elementary row operations to transform it into this, right? So we're going to focus on the sort of left half to do the actual row operations. Basically, Gauss-Jordan. We're just going to do Gauss-Jordan elimination to matrix A to convert it to its reduced echelon form, which should be the identity if it's invertible. In the same times, we'll just keep track of what's happening over here, and we'll get to the inverse. And this is called the inversion algorithm. Okay? And so in the next video, I will illustrate the inversion algorithm for you with this matrix down here.